So today we're going to discuss 4.4 properties of logarithms and the logarithmic scales. All right. There are a bunch of properties for logarithms. So I want to talk about, and here we'll just do 4 properties. The first property says, if you take the logarithm of any base of a product, and then you can break up the logarithm into a sum of 2 logarithms on each factor of the product. So log m times n base b will be equal to log m base b plus log n base b. So that's for the logarithm of a product. Correspondingly, when you take the logarithm of a quotient, it becomes a difference of 2 logarithms. So log m of n with base b equals log m base b minus log m base b. Okay, m and n can be any numbers or any functions. Okay, in those 2 properties. The third property says the logarithm of m to the p power with any base is equal to p times log m base b. So if you take the logarithm of exponential, then you can actually put down the exponent into the front of the logarithm to multiply with the logarithm of that base m. Okay. So this m can be any functions or numbers, again, as long as it's positive. All right. And the last property says if you know m equals n, these 2 numbers are equal or 2 expressions are equal, then you can take logarithm with the same base so that log m base b equals log n base b. All right. So what's the point? And the logarithm converts a product into a sum and converts a quotient into a difference and converts an exponential to a multiplication. Okay, so we can use those properties to rewrite some logarithmic expressions. For example, we can write log x y squared base 5 as log x base 5 plus log y squared base 5 using the first property of the logarithm of products. And then we can use the third property to rewrite the second term into 2 times log y base 5 as long as y is positive using the third property. Okay. Another example is we can rewrite the natural log of e squared y over z squared as ln e squared y minus ln z squared by using the second property. The logarithm of 2 quotients becomes a difference for 2 logarithms. And then we can break up into 2 terms for the first part, using the logarithm of product. So we get ln e plus ln squared y. And we can use the third property to put down 2 in the front in the second part to get 2 times ln z as long as z is positive. As you know, ln e is just the logarithm of e with base e. Remember, natural log ln means the base is e itself. So so you get 1 in the first term, okay? Because then base and the number you take in logarithm are the same. So this is one property we discussed the last time. And we can rewrite the square root of y as y to the half in second term, and then put down half in the front to get it half times ln y as long as y is positive. So it has to be positive in this case, actually. So at the end, the answer is 1 plus half ln y minus 2 ln z. Any questions about this example? No question. Let's go to the next page. Okay. So we just broke up some expression, the logarithm of some expression into several terms, but we can also, do a similar thing backwards if we have a sum or difference of logarithms. We can combine them into one logarithm as long as they have the same base. Like the examples in here. The first example we have is 2 ln x plus 1 half ln x plus 4. We can combine these two logarithms into one because they got same base e. But we have to rewrite each term, in a different expression to start. So, for example, we can pull back 2 in the front into the exponent of x to get x squared. So it becomes ln x squared. If you use the property 3 of the previous page backward. Similarly, we can put 1 half in the front into the exponent of x plus 4 to get ln x plus 4 to the half using the same property. So then we can rewrite the x plus 4 to the half as square root of x plus 4 if you want. And now we have 2 logarithms with the same base and without any coefficients in the front. So we can combine them into one by using the first property of logarithms backward. So the sum of 2 logarithms becomes the logarithm of the product. So we got ln of x squared times square root of x plus 4. All right. So that's the first example. Any questions for this example? In the next example, we got 3 terms, but they're all logarithms with same base 5. So we can combine them into one logarithm. So again, we have to rewrite each term a little bit. Actually, there's nothing we need to do in the first term because we don't have anything in the front. So just keep it as it is. The second term, 3 logarithm of 5 of y base 5, we can pull out 3 into the exponent of y, so we get the logarithm of y cubed base 5. All right, and we keep this third term as it is. Then we can combine the terms into one. You can do it one by one. You can combine 2 logarithms first and then combine the other one later, but you can also do the whole thing at one step. We know when you add 2 logarithms with the same base, it becomes a product. So we got log x squared minus 4 times y cubed. And we also know if you have two logarithms with the same base, it becomes a quotient, the logarithm of a quotient. So that means x minus 2 squared should be in the denominator. So we can put all the, these factors in one step. Then we can simplify this the expression a little bit by, canceling the common factor on the top and at the bottom. So this time we got the x minus 2. In common, if you factor x squared minus 4, you get x minus 2 and x plus 2. If you remember how to factor difference of squares. Okay, covered in math 110, 100 or 110. I think it's 100, 101, maybe 102. So then we got x minus 2 canceled. That will reduce the whole thing as x plus 2 times y cubed over x minus 2. You take the logarithm of that, then with base 5. All right. So this is another example. Does anybody have any questions for this example? We just use the basic properties of logarithm to rewrite the logarithms into different format. Okay. If no question, then we're going to discuss an important property for logarithm, and that's called the change of base formula. Okay. So it says if you try to take a logarithm of a number x with base b, you can actually take the logarithm of both x and b using another base a, we call it a, and divide those two logarithms. Okay, so this is especially important when you have a base b uncommon base like 1.3. How do you calculate the logarithm 2 with base 1.3? Then you can using some base that we use frequently, like base 10 or base e. Okay, so you can write that as logarithm of 2 base 10 over logarithm of 1.3 base 10, or logarithm of 2 base e divided by logarithm of 1.3 base e. Okay. So let's just do 2 examples to show the use of change of base formula. So in the first example, we want to compute the logarithm of 18 base 3. And we can rewrite it as natural log of 18 over natural log 3. That means we use the base e for 18 and 3. Okay, and then you can find out natural log 18 is 2.8904, and natural log 3 is 1.986. And then if we divide these two numbers, you get 2.6309. Okay. Another example is how do you find the logarithm 400 base 12? You can also use natural base. You can rewrite the whole thing as ln 400 over ln 12, and the ln 400 is just 5.9915, and the ln 12 is just 2.4849, and these two numbers divide, you get 2.4111. Okay, so this is the change of base formula. Any questions about it? So we're still discussing some basic properties of logarithms. Okay, one of the important applications of logarithms is the logarithmic scales. We can use the logarithm to measure the earthquake magnitude. So it's called the Richter scale magnitude of earthquake. And we call this M. And it's defined as M equals log ROI0. Okay, I don't know what happens to this format. It usually gives a little compatibility issue when I use PPT in Zoom. Okay, so like when you heard something saying the 5.7, the earthquake magnitude or level is 5.7. How does number 5.7 come from? It's the logarithm of I over I0, where I is the intensity of the earthquake, and I0 is the intensity of zero scale earthquake. So you just measure the intensity of the earthquake and then compare with some standard intensity I0, okay? And then you divide those two intensities and take a logarithm, okay? So for example, if the intensity of an earthquake is I equals 12,589,254 I0. So this huge number times I0, where I0 is the reference intensity, and we call it zero scale earthquake. So if the intensity of a current earthquake is 12 million times the standard intensity. So you want to know the scale of the earthquake. All right. So just use the formula, the scale of the earthquake, m equals logarithm of I over I0, but we know I is 12,589,254 I0, and then divided by I0. So I0 cancels. So again, they just take a logarithm of 12,589,254, and it turns out that equals 7.1. So you can see the number 7.1 looks like not a big number, but the actual intensity of the earthquake is really, really strong. 12 million times the standard or reference intensity of the earthquake. All right. Any questions? Okay, let's do another example about the earthquake. Compare the intensity of the earthquake in Chile in 1964, m equals 9.5. So that's a really huge one. Okay, huge 9.5. I never heard about those kind of things before. And compare this earthquake with the one in San Francisco in 1889, which is 7.1. I just did one example. I think that one destroyed the whole city of San Francisco in 1889. But the one in Chile was even stronger, okay, in 1960. So we need to compare the actual intensity of these two earthquakes. So let's just use I1, I2 to denote the intensity of the two earthquakes respectively. I1, the Chile one, and I2, the San Francisco one. So based on the definition of the earthquake, we got that log I1 over I0 equals 9.5, and log I2 over I0 is 7.1. This is just from the definition of earthquake magnitude. So if you take the difference of these two equations, left by left and right by right. So we got log I1 I0, I1 over I0 minus log I2 over I0 equals 9.5 minus 7.1. Okay, so using the properties of logarithms, the left-hand side can be written as a quotient logarithm of a quotient. So that's log I1 over I0 over I2 over I0. So that's the left hand side, and the right hand side is just the number 2.4. It will subtract 7.1 from 9.5. Now we do a little simplification for the fractions on the left. Remember, when you divide two fractions, you just multiply the reciprocal. So it becomes I1 over I0 times I0 over I2. So then I0 just cancels. So the left side just becomes log I1 over I0. And then now we can figure out what exactly the difference of the two intensities of the two earthquakes. So when we use logarithm without any number denoted, it means the base is 10. Okay, so then we can rewrite this logarithm equation into an exponential one. If you still remember what we did, a couple of classes ago. So once again, the logarithm just gives you the exponent. So the base is 10, the exponent with 2.4, and that will be equal to the number you try to take a logarithm. So that's I1 over I2. So now if we use a calculator to compute the 10 to the 2.4 is 251. So the intensity of the earthquake in Chile in 1960 is 251 times the intensity of the earthquake in San Francisco in 1889. so it's much stronger. Okay. So you can see, even a small difference in the magnitude of the earthquake means a big difference in the intensity of the earthquake. All right. Any questions about this example or the two examples? If not, let's just go to the next page. The other application of the logarithm is called the pH value of a solution. When we compare, acid or what? You can judge it from the pH value of the solution to tell whether it's an acid or something else. So the pH value of a solution is defined as the negative log of the concentration of the hydronium ion. Okay. So it's the negative log of that concentration. All right. That's how you define the pH value of the solution. So let's just do a few examples. We define the pH value of for solutions. First, an orange juice with the hydronium ion concentration of 2.8 times 10 to the negative 4 moles per liter. Okay, so the concentration in standard unit is moles per liter. So using the definition of pH value, it's just negative log the concentration of hydronium ion. So that's negative log at 2.8 times 10 to the negative 4. You can use a calculator to find out. That will give you 3.6. So When the pH value is less than 7, it's acid. Okay, so this solution is acid. So the orange juice is acid. So what's wrong with it? You should not drink too much of the orange juice because it's acid. Okay, never drink too much. This acid, the solution. All right, not too much. The second example is the milk with the hydronium ion concentration of 3.97 times 10 to the negative 7 moles per liter. Again, just using the definition of pH value, that's the negative log of hydronium ion concentration. So that's negative log 3.97 times 10 to the negative 7. And if you use a calculator, you get 6.4. So again, it's acid, but it's a weak acid. So that means it doesn't hurt too much. You can drink a lot of milk as you want. Okay, milk is good. And the third example is rainwater with hydronium ion concentration of 6.31 times 10 to the negative 5 moles per liter. Again, the pH value, the concentration is negative log from hydronium ion concentration, which is 6.31 times 10 to the negative 5. And if you use calculator, you find this 4.2. So this is also acid, rainwater, no good. All right, don't drink rainwater. All right. Now, the last example says a baking soda solution with the hydronium ion concentration of 3.98 times 10 to the negative 9 moles per liter. The pH value is just negative log 3.98 times 10 to the negative 9. The hydronium ion concentration. You use calculator, you get that number is 8.4. So that's okay. It's not acid. It's greater than 7. Though. That's not acidic. So that's good. So that's the end of this section. This is a really short section, and we just finished in one class. Do you have any questions for this section?